Ever wonder what that volt rating on a battery really means? Today, we're going to pull back the curtain on the hidden chemical force that gives a battery its power. We're going to dive into the science behind something called standard reduction potentials.
Okay, let's kick things off with a little puzzle. You've probably seen this a million times. You've got a tiny little AAA battery, and then you have this huge, chunky D cell. I mean, one is massive compared to the other, but look closely. They're both labeled 1.5 volts. How on earth is that possible?
Well, the secret has absolutely nothing to do with the physical size or the amount of chemical juice packed inside. It all comes down to a fundamental property called cell potential. Think of it as the difference in energy between the two halves of the battery.
So what is cell potential? It's the technical term for voltage. It's that electric potential difference between the two sides or half cells of a battery. This difference is what creates a sort of push that urges the electrons inside to get up and flow from one side to the other.
Here's a great way to picture it. Think of a canal lock. You've got water at a high level on one side and a low level on the other. That height difference creates the potential for the water to flow, right? A battery is basically the same thing. The high water level is the anode, which is full of high-energy electrons. The low water level is the cathode. And the cell potential? That's the height difference that drives the flow of electrons.
Okay, but this leads us to a really tricky scientific problem. A battery needs two halves to work. You need a complete circuit. A single half reaction just can't happen by itself. Electrons have to have somewhere to go. So how do you measure the individual power, the potential, of just one half?
It's a classic chicken and egg situation, right? To measure voltage, you need a complete flowing circuit with both halves. But what we really want to know is the absolute potential of each individual piece. You can only ever measure the difference between two of them at once.
So, facing this paradox, what was the clever workaround? How did scientists figure out a way to measure the seemingly unmeasurable?
The solution was just brilliant. They decided, if you can't measure something absolutely, just measure it relatively. They created a universal reference point, a baseline that everyone in the scientific community could agree on to compare everything else against. They called it the standard hydrogen half cell.
And here's the stroke of genius. They simply defined the electric potential of this standard hydrogen half cell as exactly 0 volts. That's it. They just said, this is 0. It's like marking the 0-inch point on a brand new ruler. Now, they had a starting point for everything.
And with this universal 0 firmly established, they could finally get to work. Now they could connect any other half cell to it and just read the voltmeter. Whatever that reading was, that was the potential of the new half cell, relative to their 0 point.
So let's see this in action. They hook up a zinc half cell to the hydrogen standard, and the voltmeter reads negative 0.76 volts. What does that mean? It means zinc has a weaker pull on electrons than hydrogen does. And just like that, they had the first entry on their chemical leaderboard.
Okay, next up, copper. They swapped out the zinc, put in a copper half cell. This time, the voltmeter showed a positive reading, plus 0.34 volts. This told them that copper has a stronger potential to attract electrons than hydrogen. You can see how the leaderboard was starting to take shape. So by repeating this process for tons of different materials, chemists built out a comprehensive table of these standard reduction potentials. And the core principle, as this quote says, is that the total voltage of any battery is simply the difference between the two halves. And this is where it gets really powerful, because now we can start making predictions. And it all comes down to this incredibly simple formula. The cell's total voltage is just the cathode's potential, remember that's the half that's gaining electrons, minus the anode's potential, the one that's losing them. With this one equation, you can literally design batteries on paper. Let's actually try it. Let's build a silver zinc battery right now. So step 1, we look up their potentials on our table. Silver is plus 0.80 and zinc is negative 0.76. Step 2, which one is the cathode? Just remember the rule, the higher, more positive value wins. So silver is our cathode. That means step 3, zinc has to be the anode. And finally, step 4, we just do the math. It's cathode minus anode. So that's positive 0.80 minus a negative 0.76, which gives us a grand total of 1.56 volts. See? Simple.
Here's a super easy way to remember this. Just think of it as a competition for electrons. The half cell with the higher, more positive reduction potential, it always wins. It has a stronger pull, so it yanks the electrons towards it, and because of that, it becomes the cathode, which is where reduction happens.
Now, that final number we calculate, the sign of that voltage is incredibly important. If it's positive, the reaction is spontaneous. Congratulations, you've got a working battery. If it's zero, the reaction's at equilibrium. Your battery's dead. And if it's negative, well, that reaction won't happen on its own. You'd actually have to pump energy in to make it run.
You know, let's go back to our water lock analogy to really understand why a battery dies. A brand new battery is like a lock with a big difference in water levels, a high cell potential. But as it runs and electrons flow, that level difference shrinks. And eventually, the levels are equal on both sides. The potential is zero, the flow stops. The battery has reached equilibrium, it's dead.
So let's recap the big ideas. First, voltage isn't about size, it's all about the difference in potential. Second, to even measure this stuff, chemists had to invent a 0 point, our standard hydrogen half cell. Third, using that 0 point, they built a table that lets us predict any battery's voltage with a simple formula. And finally, if that predicted voltage is positive, you've got power.
And that's really the coolest part of what we've just learned. You now have the fundamental tool that battery designers use every day. So, I'll leave you with this final thought. If you had that full table of potentials in front of you, what two materials would you combine to create the most powerful battery possible? That exact question is what drives real-world innovation, and now you actually know how to think about the answer.